Okay, so we're going to pick up where we left off last week, knock out this review. That way, by the end, we have a comprehensive packet of information. The video is in two parts. Part one was posted last Thursday. This will be posted later this afternoon if you want to go back and review anything. But hopefully we'll have a little extra time afterwards to answer any questions as needed. So we should be ready for number 17. We finished number 16 last week. Number 17, nice little softball pitch here for us for our Monday to start off, asking us to sketch the graph of the line, and the equation we're given here is that x equals 3. So this is actually one of those special cases that we came across, and I'm going to go ahead and identify both of them because you don't know whether it's going to be a horizontal or a vertical line on the final tomorrow, so we'll just consider both cases. So off to the right here in the margin, a couple reminders. You know it's a horizontal line if the equation is y equals some number. So no other variables, no other numbers, just y equals a number. That's going to be a horizontal line. The opposite of that, of course, is going to be a vertical line. Which is x equals some number. At which point then we find that value, draw on our vertical line. So these are the only two special cases that we came across. All the other linear equations that we came across was typically in slope-intercept form, that y equals mx plus b. But these are the two that kind of crept their way in there every once in a while. They are the easiest ones to graph, take the least amount of time, but they're also, because they're so similar in style, they're also the easiest ones to switch up, to mix between the two. So in the case of number 17 here, which case are we looking at? Horizontal or vertical? Vertical. It is vertical because we have x equals some number. That number in this case is 3. So this is how easy it is. You literally find 3 on the x-axis, since that's what x equals. And that is the point through which we're going to draw our vertical line. I don't like how skinny that is. It's kind of hard to see. Oh my gosh, that's too much. Still too much. It's Monday, so I'm extra picky. There we go. So x equals 3 gives us the vertical line through the value of x at 3. So not a whole lot of work there other than just recognition. Number 18. Number 18 is asking us to write the slope-intercept form of the equation of the line which passes through the point -5, 5 and is perpendicular to the line y equals 5/9 x minus 4. So let's pick out some of that information. First off, we want to make sure, or at least we'll know we're done when we reach slope-intercept form, which, quick reminder, yet again, is y equals mx plus b. That's where we're aiming for. But then when we pick through the information we've been given, we were given a point, and we were told that it is perpendicular to a line that they gave us the equation for. So we'll start with the easy bit of information, that point. Anytime we've been given a point in the past dealing with lines, we usually labeled them as x and y, or if we have multiple, typically we use x1 and y1. But then we're given this information that our line is perpendicular to another. Now, who recalls what it means to be perpendicular?
Have the same slope.
Ooh, careful. So Leanna, you actually said two words. You said the word opposite, but then later you switched it to reciprocal. And then Tiara said the same. Now, there were actually two types of relationships we learned in the same lesson. So this is where all of that information is actually kind of being lumped together, but we want to pick out the information that ties to perpendicular lines specifically. So which is it, Leanna? Is it opposite or is it reciprocal? It's a trick question. It's both. Perpendicular lines have opposite reciprocal slopes. We change the sign and we flip the fraction. So perpendicular lines have opposite reciprocal slopes. Now, Tiara, to bring it full circle, what types of lines have the same slope?
Parallel lines.
Parallel lines. So there is a chance on tomorrow's test, you could have a problem just like this, but it could say, instead of perpendicular, it could say parallel. So I'm going to put a little side note in here. On that off chance that this happens, to remind you that parallel lines have the same slope. So that's not going to affect us on this problem. Our lines here are perpendicular, but these were both lumped into the same lesson. So it's good to be prepared for either one. But let's go back to what that means again. Opposite reciprocal. So if we refer back to the lesson in which we did these, this is where we pulled out the slope we were given and adjusted it to be the opposite reciprocal we needed. So in this case, what is the slope of the line we were already given? 5/9. So the slope we were given was 5/9. Now that is not the slope we want because our lines are not parallel, they are perpendicular. So instead, we want the perpendicular slope, which in this case would be you got the reciprocal -9/5. So there are two changes that have to take place. The sign has to change. So in this case, the positive slope becomes negative and the fraction has to flip. Now remember, if it doesn't look like a fraction, make it look like a fraction first by writing it over 1 so that you can have that flip to get the reciprocal. So here's the slope we're going to use, along with the point we were also given. Now, quick side note, because this sometimes distracts some of my students. What about that -4 in the equation? Where are we going to use that? What is it? It's the y-intercept. Now let me ask you this. Is it the y-intercept for the line we're looking for? Or is it the y-intercept of that line? Of that line. I don't really care about that line because we already have the equation for it. And we already took out the slope, which is really all that perpendicular really talks about is slopes. So just a quick reminder, this is extra information. You don't actually use it. We don't need that. It was important for that particular line, but that's not the line we're looking for. All we needed to know was what our slope would have to be in order for our line to be perpendicular. So now when I take a step back and I consider the information I now have a point from my line. I now know the slope of my line. This, and we had one of these earlier in this packet. This sounds like a prime candidate for that secondary form that we used, which was called point slope form. A point slope form, in case you have forgotten, because it's been the weekend, is y minus y1 equals m times x minus x1. And if you notice, hopefully everything for the most part should be labeled accordingly to be able to drop them all in to their appropriate spaces. So if I was to do that here, I would have y minus y1, which is 5, equals m. I want to make sure I use the slope that we came up with, which was the negative 9/5. And then in parentheses, x minus x1, which is a negative 5. Now, if you recall, I'm kind of picky here. Let me zoom in a little bit. Anytime we have a double negative, I highly recommend rewriting it so it looks like addition. Because for a lot of students, most of my students, having a double sign there can cause a bit of a headache, which opens up the opportunity for mistakes. So if I was going through this one myself, I would take one extra line here, and inside the parentheses, I would rewrite that as x plus 5. Now, good news is we have our equation. Bad news, what form do we need it in? Y equals mx plus b. We need it in slope-intercept form. So we're not quite done yet. Hopefully the first thing that's catching your attention would be what? Those parentheses. We don't typically have parentheses in slope-intercept form. So to knock them out, let's go ahead and do a quick distribution. Negative 9/5 times x, that's the easy one. That's just negative 9/5 x. But the second one requires a little bit of thought. Now, if you have a calculator, and I've shown you how to use the fraction functions on there, great. If you're not quite sure of how to use those, or you don't have a scientific calculator, the mental trick I use is I take this whole number, 5, times the numerator. So 5 times negative 9 would give me negative 45. Take that negative 45 and then divide it by 5. You get a negative 9. So negative 9/5 times 5 comes out to be a negative 9. Bring down my equals, bring down my y minus 5. It's looking a little bit better, except for one issue. We have the y minus 5, whereas in slope-intercept form, y is typically where? Or what's special about it? What do you have the urge to do here? Move the negative 5, because don't we want the y by itself? Yeah. So how would you move that negative 5? Add 5 to both sides. So that drops it from the left, leaving us with y equals the negative 9/5 x falls down. We didn't mess with it. Negative 9 plus 5 should give me a negative 4. So if I slide over here to my answer line, my equation is y equals negative 9/5 x minus 4. So again, there will be a problem like this on the test tomorrow. The only things obviously that would switch would be the numbers. The values are going to change a little bit. There is a chance though that instead of saying perpendicular, it may say parallel. I honestly don't remember which one it is. But so long as you remember that perpendicular lines have opposite reciprocal slopes, parallel lines have the same slope, you're set for either scenario. All right. Number 19. sketch the solution of the system of inequalities. First off, system, if you remember from that unit, unit 3, is when we dealt with 2 or more of something. So in this case, we have 2 linear inequalities. Now, inequalities are the ones where we didn't mess with substitution or elimination. We stuck specifically with graphing. Now, in order to graph these, what form would I like them to be in? I'd really like them to be in slope-intercept form, because only then can I pull out all the information I would need for both to be able to get them on the graph. So a little side note here. They need to be in slope-intercept form. Before graphing. Otherwise, you're just going to be taking a shot in the dark as to what your slope is, what your y-intercept is. There's no need to guess in this class. We have the skills necessary to be able to work through these. So what I'm going to do here, just because we're going to need some space, because unfortunately, neither one of them are in slope-intercept form, is I'm going to copy them down here below, giving me plenty of space to work with. So the top one, I'm going to write down first, 4x minus 3y is less than 9. And then over here to the right, I'm going to write 1x plus 3y is greater than or equal to 6. Set up my workspace here a little bit. Then put in some guidelines here, because similar to equations, we can manipulate them by moving pieces around. I think we're about ready to go. So I'm going to start here on the left. 4x minus 3y is less than 9. Slope-intercept form is our goal. So if we wanted to oversimplify that, we're trying to get y by itself. What would you move first?
4x.
4x. So since it's a positive 4x, I'm going to use a negative 4x on both sides. So 4x, take away 4x is gone, leaving me with negative 3y is less than. Now remember, if they aren't like terms, don't force them together. Don't try to combine them into something new. 9 and negative 4x are not like terms, but that's okay because I know I'm going for slope-intercept form. So I'll just write negative 4x, and after that, I'll write the positive 9 that was already there. Just bring them on down. What's next to move?
The negative 3.
The negative 3. How would we move it? Divide it. Now I got to remember, I'll zoom in here because I want to make sure we get all this information in here. We are dividing everything on the left by negative 3, which means to keep it balanced, we have to divide everything on the right by negative 3 as well.
Don't you flip the inequality?
Good question. Leanna asked, don't we flip the inequality? Why do you feel like it should be flipped?
Because we're dividing by negative 3.
Because we divided not specifically by negative 3, but a negative in general. So anytime you multiply or divide an inequality on both sides by a negative value, that sign does change direction. So good catch there. So we do have our y by itself now. The less than symbol is going to switch on us to a greater than symbol, and that is from dividing by the negative. And then I need to go through and clean up the right-hand side a little bit, simplifying where I can, dividing where I can, watching my signs carefully. Unfortunately, 4 doesn't divide nicely by 3, but because they're both negatives, double negative always turns what?
Positive.
Always turns positive. So I'm going to keep that as a positive 4 over 3, because that's as simplified as that one will get. Don't lose your x. And then 9 divided by negative 3
Negative 3.
is a negative 3. So now with a little bit of effort, we have our first inequality in slope-intercept form. And from that, we can list the 4 pieces of information we will need in order to get it on the graph. So I'm going to write that down below here. First off, in the order that we're going to use them, what is the y-intercept?
4/3. Oh,
Four-
wait, -3. Sorry.
-3 is our y-intercept. What is our slope?
4/3.
4/3. Okay, then focusing on that inequality symbol, which hopefully we remembered to flip as we did here. What type of line is that going to give me? It's going to give me a dashed line. And with respect to that dashed line, are we going to be shading above it or below it?
Above.
We're going to shade above it. Good. So my recommendation, before jumping to the second one, and then having 8 pieces of information to kind of sort through, why not see this one through and get it on our coordinate plane? So our y-intercept here is going to be a -3. So find the -3 on the y-axis, put your first point. Our slope is 4/3, which has us traveling where from the y-intercept?
Up 4/30.
Up 4, so 1, 2, 3, 4, and then to the right 3.
Yeah.
1, 2, 3. So that has us landing right here, and I think I can actually squeeze one more in that direction. Put it right, hit the edge of the graph. Sometimes I can go the opposite direction, in this case down 4, left 3, but that's going to run me off the edge. So this one's about as far as it can go. According to my inequality sign, this line should be dashed. So I'll go ahead and draw in a dashed line. And remember, we have a whole second one coming. So if you are going to shade lightly here as a reminder, do it super lightly because we're not going to need everything at the very end. So just as a reminder, what I usually do is just very lightly identify which side of the line we shaded on with respect to this one. Because when I come back later, we're going to have to put a second one over top of it. So there's the first inequality, linear inequality, graphed on our coordinate plane for us. Then we come over, we take a look at our second one. Working towards slope-intercept form yet again, what would we move first? The x. So I'm going to subtract that 1x from both sides. Which removes it from the left-hand side, leaving me with 3y is greater than or equal. Those aren't like terms on the right, so I just bring them on down. So bring on down the -1x. Next to that, I'm going to bring down the +6. With that -1x out of the way, what do we still need to move? The 3. So we divide everything by 3 here. Now, is my sign going to flip?
No.
No, not dividing by a negative this time. So the greater than or equal to sign is safe here. It's going to stay greater than or equal to. So I have y is greater than or equal. -1x divided by 3 is going to stay -1/3 x. And 6 divided by 3 should give me a +2. With a little bit of effort, this one is now in slope-intercept form as well. So with it in slope-intercept form, we can start pulling that information out like before. What is our y-intercept?
2.
A +2. What about our slope?
-1/3.
-1/3. And then looking at the inequality sign, which is a greater than or equal to symbol, what type of line is that going to give me? It's going to be a solid line. And with respect to the solid line, which side am I going to shade on?
Below.
Ooh, careful.
Above, right?
Above. The greater than part gives me above. So with that information now, I can start putting that on my coordinate plane. So the y-intercept is at +2. So at +2 on the y-axis, put a point, our first point, with a slope of -1/3. Where are we going to travel from there?
Or down 1 over 30.
Down 1 to the right 3, which we actually already have a point there. So I'm going to go down 1, right 3 again. And just so I can see it, I'm going to also go up 1 to the left 3. So I got a really clear idea of where my line is traveling. Thanks to the inequality sign having the equal to part, this is where we draw in our solid line. And with respect to that solid line, we are going to shade above. Now, again, just very lightly, I put in my shade for that one because we have to remember what we really want is where we ended up shading twice. So if I look at, all the information I was given here, the region we want had better be above both the dashed line and the solid line. So if I was to zoom in here, that would only include this region up here, which hopefully you can tell is the only region that I have a little bit of shading from both inequalities. Now, I'm not super picky when I'm grading these, so long as it is very clear which region is obviously your darkest and therefore your final answer. Now, if you're like me, kind of, I don't know, obsessive, I usually go through and I erase any extra. That way there's no question as to where my final region is. But that is the final solution. All the points in that shaded area are considered solutions to this system of inequalities, which means, just to quickly summarize, if I were to take any point in this region and plug in the coordinates into either one of these inequalities, it would come out as a true result for both, but only for points in this region, or this region does continue off because the lines do go on forever. Number 20. Number 20, I don't know why, but every once in a while I have a student who is in a hurry and misreads this one, I think, because it does simply just say simplify. But for whatever reason, I have a lot of students miss this subtraction sign here in the middle. And in their head, they imagine that these two trinomials are being multiplied. So they set up a 3x3 box, they fill it in, it looks great, it looks fantastic, but that is not what we're doing here. We are not multiplying these trinomials, we are subtracting. Now, if you went back to Unit 4, towards the beginning of Unit 4, you may recall that subtraction really relies heavily on just combining like terms, with one big exception. Everything following the subtraction sign is deceiving because their signs aren't actually as they appear. And my recommendation was imagine that subtraction sign is a -1. Anytime we have a value other than a +1 outside a set of parentheses, our instinct, hopefully by now, is to distribute. And when I do that here, everything inside the second set of parentheses, all the signs are going to switch. So -1 times -12 is going to give me a +12. -1 times +5x is going to give me a -5x. And -1 times 6x squared is going to give me a -6x squared. Now, if you're wanting something similar for the first one, you can technically imagine that there is a +1 there. But does multiplying by 1 change anything?
No.
No. So really, for our purposes, I could just bring them down as is. So 5 plus 7x to the third plus 3x to the second. And from there, all that's left is to combine like terms. Now, I really like descending order, so I'm going to look for the highest exponent and work my way down from there. And it looks like we have a 7x to the third. Is there any like terms to combine with 7x to the third? No. So if there's nothing to combine with it, it's not going to change. I just bring it on down and move on to the next power, which is going to be x to the second. First one that catches my eye is 3x to the second. Does it have any like terms?
Yes.
What do you see?
-6x to the second.
-6x to the second. Okay. Now, if you were to combine 3x to the second and -6x to the second, what would you get?
-3x.
-3x. Do I change the exponents?
No.
No. Anytime you're combining like terms, don't touch the exponents. The only exponents that change, excuse me, the only time exponents change is when we're dealing with multiplication and division. Like terms is just addition and subtraction. Moving on through my list here, x to the power of 1, I see a -5x. Of course, that exponent of 1 is hiding as usual. Any like terms to combine with it?
No.
No. So I bring it on down. And then last but not least, we have our constants, which have no variable attached to them. I see a +12. See anything else?
+5.
There's also a +5 all the way here at the beginning. Sometimes it's easy to overlook things. 5 and 12 make
17.
17. And just like that, we just subtracted one trinomial from another, and we ended up with a very nicely written polynomial descending order by combining everything that we possibly could. Any questions on that one? Or any of them on that page for that matter? We can always come back if we need to. Number 21, the dimensions of a rectangle are 2m plus 3 and m plus 4. Write an expression that models the area of the rectangle and simplify if possible. Well, some things that I would pick out there very quickly is that it is talking about the area of the rectangle. And how do you find the area of a rectangle? It's Monday, we're stumped, or we're just tired. I'll help you guys out. Area of a rectangle is length times width. And length and width, general term for those are its dimensions. But we were given the dimensions as two binomials, 2m plus 3, which I could say for our purposes is our length, and m plus 4 for our purposes could be our width. Therefore, to find the area, I would take the 2m plus 3 and multiply that with the m plus 4. So long story short, it was just a really fancy way of asking us to multiply two binomials together, which we spent a lot of time doing in Unit 4. And it's at this point, this is where we typically would use a box. And this box is going to be 2 by 2 because they're both binomials. I'm going to put the 2m and the positive 3, which is my first binomial. I'm going to use that to label my rows. And then I'm going to use the m plus 4 to label my columns. And to make sure I've multiplied everything, I just need to make sure that every row is multiplied with every column, or in other words, every square is filled. So starting here at the beginning, 2m times m gives me what?
2m to the second.
2m to the second. Going to the right, 2m times 4
8m.
is 8m. Going to the second row, 3 times m
3m.
is 3m. And the last square, 3 times 4
12.
gives me 12. And my favorite part about the box is that if you check this diagonal, typically, not always, but typically, you're going to find some like terms, which is really handy when you're going to write out your final result. You can just combine those straight away. So for our area of this particular rectangle, we can write the expression 2m squared. 8m and 3m make
11m.
11m. And then the 12 jumps there on the end. So again, it didn't come out and say, hey, multiply these two binomials together. Instead, what it did was it took our past knowledge of what it means to find the area of a rectangle, what dimensions are, and then once we figured that out and pieced all the information together, well, then it turns out, yeah, we're just multiplying two binomials together. Number 22. Number 22, still dealing with polynomials here. This time we are dividing. Now, if you recall from the lesson where we talked about our 4 operations dealing with polynomials, you'll recall that we only really worked on dividing by monomials, which is the case we have here. Now, you may also recall that when it was written out in this horizontal format, it was kind of harder to see just exactly how these pieces are going to interact with each other. And it was at this point, my recommendation was simply rewrite it. So instead of seeing it as dividing an entire trinomial by the monomial 4n, instead imagine that each term from that trinomial individually is being divided by that monomial. So for our purposes, it's kind of like I said, okay, instead of writing it this way, let's write the same problem of division, still division, but use little fraction bars as our division instead of the division symbol itself. And the reason I like this is because then I can just go in and divide each term one at a time. I'm going to start at the left. Does 2 divide nicely by 4? Not nicely, no. Does 2 over 4 simplify as a fraction? No.
Yeah.
It becomes 1/2. What happens to my exponents when I divide common bases? What do you think n to the third divided by n is going to become? I'm going to take an educated guess. Close. You had 2 directions you could go, and unfortunately you went in the direction of multiplication. So multiplying common bases, we add the exponents. Dividing common bases, we subtract. And if it helps, if you need to see it, you can imagine that the exponent down here on the 4n is a 1. So n to the third divided by n to the power of 1 is going to leave me with n to the power of 2. Technically, I guess it should go on top. Every time we combine, we always put them on top. Moving on to my second term, 8 divided by 4 is going to give me a 2. N to the second divided by n is just going to give me n. And moving on to the last term, 12 divided by 4
Just 3.
is just 3. Are you saying just 3 is in like there's no variable?
Okay.
Good. So there was only 1 in there. We took 1 n away. There's no more n's left in the third term. So this is our result.
Now, on the test, if we write the into the second with the 2, would you count us wrong? So that's a little frustrating writing it like that.
So technically it would be wrong because the only reason, so in case Marissa didn't catch it, the question was, would it be wrong if the n to the second power on the first term was written down with the 2? Technically, that would be incorrect because the only reason we move something from the top to the bottom is if what happens to the exponent. Remember? We only typically did that for negative exponents.
Okay.
So by default, they should land on top. Now, some people write them to the side. That's technically the same thing. But it cannot be written next to the 2 because that only would have happened if we had n to the power of -2, in which case we would have brought it to the other side of our fraction. So technically, yes. Now, sometimes, depending on my mood that day, I will circle it, make a note of it, but not count off on it. But technically, yes, mathematically, it's wrong. Good question, though. Not often do I have students catch that key difference. All right, number 23. 23 is a word problem, so we need to sift through the information we're given, make sure we're working with it accordingly. It says that Robert owns a t-shirt shop near the beach. He pays $1,000 each month for rent. It costs him $10 to make each t-shirt, and then he can sell them for $24 each. Here's a question. Usually that's very important because then we know what we're looking for. How many t-shirts must he sell each month in order to make a profit? So important. In fact, I think I'm going to even highlight it. How many t-shirts must he sell each month in order to make a profit? Well, a word in particular that jumps out to me is profit. What does it mean to profit?
Make money.
To make money, to actually come out ahead. Now, at the start of each month, is Robert ahead? No, because what does he have to pay for right off the bat?
Rent.
Rent. So he pays his rent. And then in addition to that, he also has to pay for supplies. He starts off in the negative. So he needs to know how many shirts he's got to be selling each month in order to, at the very least, break even before making a profit. So if you were to break this down into two categories for Robert's scenario, he's doing two things. He is spending money and he is earning money. Now, in order to make a profit, which one has to be greater? The spending or the earning?
Earning.
The earning. So the spending had better be less than the earning. Or if you remember, the little alligator likes to go towards the bigger one. This little alligator is eating the earnings because we want this one to be bigger. Now the trick is we need to pull all the information to figure out which of that information up above had to do with spending money and which information had to do with earning money. So we'll start with the spending. Toby already kind of answered this earlier, but what is the first thing he spent money on?
Rent.
Rent. And that was just one time for the month, right? And a month is the only window that we're really considering here. So every month he spends $1,000. That's guaranteed. Is he spending money on anything else?
$10 to make a shirt.
$10 to make a shirt. Now, we don't know if that's for the material, the time. We don't know what that is, but we know each shirt, when you factor it out or we figure it out, $10 per shirt. So that's in addition to his $1,000, right? Now, is that only an additional $10 one time?
No. That's per shirt.
That's per shirt. Do we know how many shirts he's selling or making for that matter?
No.
No. What's a good thing we use? What's a really handy tool we use for unknown
X.
values? X or variables in general. So we could do X. Some might use T to fit t-shirts. It's up to you. Is he spending any other money? No. $1,000 for rent plus $10 per shirt to make. Okay. If I bring down my less than symbol, what is he making? How much is $24 per shirt? And again, we still don't know how many shirts, right? So there's my X again. So he spends $1,000 plus $10 per shirt. He earns $24 per shirt. And we want to make sure that his earnings turns out to be the bigger one. Or in other words, the spending is less than the earnings. So without really just making a fuss of it, what we just did kind of accidentally was we wrote an inequality. 1,000 plus 10x is less than 24x. And if it helps, we can remind ourselves that x equals the number of t-shirts in this situation. Now, we need to solve. So it's an inequality. We solve them real similar to equations. Do you see any parentheses?
No.
Nope. Any like terms?
No.
Nope. Is the variable on both sides?
Yes.
Yes. Which one would you suggest we move? Goes against your grain.
Question, because you already know it.
I know you want to move everything to the left, which would leave you with a 0 on the right, and it can be done. I would recommend personally, I would move the smaller one here, which would be the 10x. So I personally would subtract 10x from both sides to get that variable to one side, so we then can get it by itself. So that leaves us with 1,000 is less than 14x. What's left to do?
Divide by 14.
Divide both sides by 14. Now I seem to recall it's going to give you a fraction or a decimal depending on what your calculator is telling you. What do you get?
71.428.
71.428, and I assume that goes on still, right?
Yes.
Is less than our x, or in other words, running into my other problem here. In other words, x needs to be greater than, if I write my x first, 71.428, so on and so forth. So if I were to ask you then, how many t-shirts does he have to sell? 72, which is interesting because you went against the rules of rounding, because technically 71.4 would round down.
But he wants to make a profit, so you have to round up to make that profit.
Good. So this is where one of those tricky things where the inequality sign overrules our rounding. So even though rounding would tell me to go down, the inequality says, no, it has to be greater than that amount. So we would have to round up. So in order to make a profit, he would have to sell at least 72 shirts. Now, if he sold exactly 72 shirts, did he make that much of a profit? No. But at least he made something. He at least made his money back to try again next month. Good. Go for it.
How would you find out like how much profit he would make if he made so the 72 shirts?
How much, that's a good question, actually. How much profit would he make if he sold exactly 72 shirts? Well, if we think about it, if we come back here to his spending and his earnings, we know that his rent would be 1,000 plus 10 times 72, which is 720. So his spending would be $1,720. His earnings would be 24 times 72, which is 1,728. So if he sold exactly 72 shirts, he's making a profit of $8, which doesn't sound exciting, but it does mean that he paid off his rent, he paid off the materials, and he's got an extra $8 at the end of the month. Obviously, a stronger business, you would want a bigger profit, but what a lot of people don't realize is businesses typically operate in smaller profits each month, which they then roll back into their company. And that's how companies slowly grow. So yeah, he only made $8, but that's also him paying off rent and him paying off everything else. So it's not a silly question. That's an excellent question. All right, number 24. There's that word again, factor. Now I know we've had a weekend between the first half, but just a quick recall. We wrote all things about factoring back on page 1. And in this case, I see 4 terms, which tells me I'm probably going to use grouping. Now, quick reminder, regardless of what type of factoring you're going to use, what should you always be checking for first? Always check for that greatest common factor. But from the past, what we typically realize is anytime we are factoring by grouping, usually the more terms you have, the harder it is to find the greatest common factor that works for all of them. So in this case, I'll save you the headache, and I'll tell you that there is not a greatest common factor, at least not for all 4 terms. So we jump straight into splitting it into 2 groups where we can hopefully find some smaller greatest common factors for each. So if I start here on the left, what greatest common factor could you take out of both 12x to the third and 3x to the second? Okay, I would agree on the 3, certainly, because 3 is the greatest common factor of 12 and 3. Why did you say just x to the second?
Because you can take x out of the second. On the last one, because that's all the x's that has to be.
So you're telling me I can't go any greater than that because of the second term here.
Yeah.
You can't take more than what the smallest amount has. And that sounds good to me. So if I were to factor out that side, I'd set the greatest common factor to the side. So there's my 3x to the second. And then I would divide. 12x to the third divided by 3x to the second would be 4x. And then 3x to the second divided by 3x to the second would give me a positive 1. Then I transition over to the second side. Now, it's at this point, it may be worth noting that with grouping, I'm happy when the binomials inside the parentheses perfectly match. that might encourage us to think a little bit more carefully on this second half. So on the right-hand side, what's the greatest common factor of negative 20x and negative 5?
-5.
Negative 5. I'm very intrigued. Why did you choose negative instead of just 5?
Because the negative divided by negative equals a positive, and you want to positive 4x plus 1.
Okay, so to summarize, just so anyone who watches this later, you said that you kind of thought ahead, it sounds like, knowing that a negative divided by a negative in either of these terms would give me a positive result, which looking ahead, if I want the binomial to match, I want them both to be positive. So that is spot on. If we divide out a negative 5 from both terms, we should get a positive 4x and a positive 1 left inside. Now, the reason why I'm happy when they match is because if I go one step further and imagine that these two halves shared the greatest common factor of 4x plus 1, I could get two unique binomials. Because anytime we set aside a greatest common factor, we always do that first before we divide. But in this case, a binomial divided by itself, as with all things, divide anything by itself, you get 1, which makes them disappear. What we're left with is going to give us our second binomial. And in this case, what is that second binomial?
3x to the second minus 5.
3x to the second minus 5. And that one, ladies and gentlemen, is now factored. Took a little bit of work, but we got it. All right, number 25. Now, number 25, technically, we never covered specifically in class, but it is one that will come up in Algebra 2 in a slightly more advanced situation. But it is one that is, when you know the definitions, becomes actually significantly easier. So the question is, what is the domain and range of the given relation? And you'll notice that the relation is just a set of 4 different ordered pairs. But then it has a second question as to whether or not this relation is a function, asking us to then explain. Now, like I said, if you know the definitions of domain and range, finding them then just becomes fairly simple. So the definition of domain is the set of all x coordinates. The set of all x coordinates. Well, ordered pairs all have x coordinates. And in this case, what are the x coordinates that we see? 11. -3. 4. And 10. There's your domain. Now, if you were to guess, what do you think the range is? It's the y coordinates. So the range is the set of all y coordinates. And what are my y coordinates here? 2, 3, 0, and another 3. Now, depending on who you ask, technically you don't have to list the same one more than once. But in my opinion, it doesn't actually matter if you do list them more than once, because it kind of gives you a better representation of what you were given to begin with. Now, there's 2 of the 3 points right there, just by splitting up the x coordinates from the y coordinates. The last point comes from determining whether or not it is a function. And this one I'm actually going to answer for you, because the explanation kind of incorporates the definition of a function. So this one, I would say that yes, this is a function because none of the x coordinates repeat. Now, sometimes students say, well, wait, Josh, there's 2 3s in the range. And I'd say, yep, I said what I said. None of the x coordinates repeat. I don't care about the y coordinates. So long as none of the x coordinates repeat, what you're looking at is considered a function. That I simplified it down?
No, on my little college test thing, they ask you the same question, and from what I was reading, I put the same answer, and they're like, "No, incorrect."
Maybe the wording was a little bit off.
I typed in the X does not copy itself.
Maybe they were looking for something more specific. All right. Number 26. We're on a roll here. We're going to have a decent chunk done before our break. Number 26 is one of those ones that's a little bit deceiving because all that it says is simplify. And what we have is a binomial raised to a power of 2. Now, I'm going to ask you, can anyone guess what the most common mistake is here?
I want to distribute.
You want to distribute. And I would say that that would be great if this was a monomial. We can distribute exponents into monomials. Unfortunately, this is the binomial. So you cannot just square 8x and you cannot just square the 3. You really have to think about what it means to raise something to a power. So if I was to ask you, what's 5 squared?
25.
How'd you come up with 25?
5 times 5.
5 times 5. You took the base and you multiplied it with itself so that there were a total of 2 of them, right? That's still what exponents tell us to do. So when we have a binomial raised to a power, what that is essentially telling us is that we need to write that binomial the same number of times that the exponent tells me to. So this would be rewritten as 8x plus 3 times 8x plus 3. There should be 2 of those binomials multiplied together. Now, hopefully you look at that and think, wow, that looks real similar to that area of a rectangle problem we did earlier where we had a binomial times a binomial, to which I would say you're absolutely right. In which case I would set up a box. And I would label my rows and columns using those 2 binomials. Now this one seems a little less interesting because they're the exact same binomial, but something special is still going to happen here. Now, before I jump into it, if I made the most common mistake, I would have probably ended up with a 64x squared plus 9. But watch what happens when we multiply it correctly once we've considered what exponents actually tell us to do. So as I'm filling in these squares here, top left corner, 8x times 8x is 64x squared. Okay, that's not surprising. That's what we would have gotten if we just squared the 8x. Then I go to the right, 8x times 3 is 24x. Going to the second row, 3 times 8x is another 24x, and 3 times 3 is 9. Well, there's that 9 I was predicting I'd get as well. But here's what we would have missed if we had simply tried to distribute that exponent. We have two like terms, both 24x's, combined make 48x. So if I was to write this out all together here, I would have 64x squared plus 48x plus 9. If I simply distributed, I would have lost this term completely, and I wouldn't have gotten all the points. You get some, but not all. I think we can squeeze at least one more in, if not two, before we take a short break. This next one says factor out the greatest common factor. And that's all we're going to do. We're just going to look to see if there's a greatest common factor we can take out. Now, I know it's multiple choice, but don't get distracted there, because it might influence you to answer one thing when you probably would know better if you were just solving it out independently. So we have a trinomial, which means whatever we decide has to work for all three terms. Now, instead of trying to figure it out all at once, do it individually, starting with the coefficients. 2 would be a good greatest common factor for 8, 8, and 10. Then move on to one of the variables. I'll start with the x's. X to the second. Why can't I go more than that? In which term?
The first one.
So the first term only has 2 x's to give. All the other ones have more, but I can't give more than what the smallest amount has. What about my y's?
You can take out one y.
I can take out one y. Okay. Now, if I was just doing this from scratch, I would write that greatest common factor off to the side. Before I divide, 8 divided by 2, 4. X to the second divided by x to the second is gone. Y divided by y,
Gone.
also gone. So I move to the second term. 8 divided by 2
4.
gives me another 4. X to the fourth divided by x to the second
X to the second.
leaves me with x to the second. Y divided by y,
No y.
y is gone. Negative 10 divided by 2
-5.
is a negative 5. X to the seventh divided by x to the second
X to the fifth.
is x to the fifth, and y divided by y
Gone.
is gone. Well, hopefully,
E.
you're saying C looks good to me. So don't be distracted by the multiple choice, because if you were looking here, 3 of the 4 all had the same greatest common factor. Where it would trip you up is in the actual division process itself. So my recommendation, just factor it all the way and then check the options you're provided. I'm gonna vote for one more because I think that's gonna be a good place to take our break. Number 28. Yet again, there's that word, factor. And as I'm looking at it, I realize, well, this has 3 terms. It's a quadratic trinomial. So I'm thinking maybe the asterisk method. Again, if you're not quite sure, you can always go back to page 1 where we talked a lot about factoring. But in this case, I'm going to recommend the asterisk method. But before I worry about the asterisk method, what should I always check for first?
Greatest common factor.
A greatest common factor. Do you think you spot any?
No.
No. What's your tell? I'm curious what you saw that made you confident that there's not a greatest common
Because
factor.
3 is only 3 times 1.
3 is 3 times 1.
3 can't go into 7 easily.
Right, because 7 only has factors
Of 1 and 7.
1 and 7. Do you know what we call 3 and 7?
Prime factor.
They're prime numbers.
So,
which means they only have factors of 1 in themselves. And that means that 3 and 7 only share a factor of 1. So for our purposes, no greatest common factor that we could use here. So then I jump into my asterisk method, and for that I need it in descending order, which we're in luck, it already is. And from that I need my A, which is 3, my B,
20,
which is 20, and my C
-7.
is a -7.
20. Top is -21.
Right, so let me set up my little asterisk here. So on top is A times C, so we're looking at 3 times -7, and I got set is a -21. Either side of that is A, which are my 3's. B on the bottom is 20. Now, if you had your factor pair list handy, that would be a great tool here, or maybe you spot them already, because there's not a whole lot of factors for 21. But I need two numbers that multiply to equal -21, but also add to equal 20. There's only two factor pairs possible for 21. Those are 1 and 21 or 3 and 7.
One and 21.
1 and 21. Okay, that would certainly multiply to give me the 21. Now, how can I play with those signs so that when I add them, they equal a positive 20,
-1.
a -1? So -1 times 21 gives me a -21. -1 plus 21 gives me a positive 20. So that finds me these two special pairs, which are going to help me find my binomials. But before I write the binomials, do either of them simplify in any way?
Yes, 3 and 21.
3 over 21 becomes
1, 7.
1 and 7. What about the 3 and -1?
No.
Nope. Bring back your variable, which in this case is the variable x, and write the top values in front of the bottom values to get what two binomials?
3x minus 1.
3x minus 1 and
1x minus 7, or plus 7.
1x plus 7. And that one is factored. Now, before we go to break, just a little quick surprise here. Number 29 says graph the following exponential function. Guess what? We didn't do that. That is something that you'll spend quite a bit more time in Algebra 2. If we had more time in Algebra 1, we would have spent a day on this. But because of the term being a little bit shorter, you do not have to do number 29. So when we come back from our short break, we're going to be ready for number 30. All right, number 30 here says, again, to simplify, but if you look at this problem, what it's basically having us do or use is going to be our exponent properties. So the exponent properties basically told us how we were able to manipulate things, change the way problems looked anytime that you had exponents in the mix. Now, with the word simplify, in terms of the exponent properties, some things that you kind of want to check for is you want to make sure that that each base, actually, let's go in the order. You want to make sure that there are no parentheses. Only one of each base. And absolutely no negative exponents. if you can ensure those three things, odds are you've probably simplified it efficiently and effectively. I kind of try to write them in the order that you would address them. And you'll notice yet again, our favorite friend, parentheses, comes at the top of that list. So that's going to be the first thing that I take a look at here on this problem. And I'm going to kind of work this one out more horizontally. I know it's not quite how I usually do things, but because of the numerator and the denominator, it'll be a little bit easier to track those pieces. But in this case, Leanna, your instincts were right in this scenario, because since there's no addition or subtraction inside the parentheses, this is just a monomial. It's a big monomial, but it's just a monomial, which means every base inside this monomial that is currently sharing the exponent of 2 can get its own exponent of 2. So what that would look like is we would have 3 to the power of 2. We would have x to the power of 5 raised to the power of 2. And we would have y to the third raised to the power of 2. And then that entire thing, again, because I didn't touch it, I'm just dealing with the parentheses right now, is I'll have the x to the 10th, y to the 8th still there.
So basically, all you're doing is distributing the 2.
The exponent of 2. Yep, every one of those bases, the 3, the x to the 5th, the y to the 3rd, all now have their own exponent of 2. I haven't actually used it yet, but I just showed that distribution.
So it was basically just distributing,
But with exponents, which
Yeah.
kind of follow their own set of rules. Now, again, just a quick recall, I could not have done that.
Josh, you want candy?
No, thanks. I could not have done that with any addition or subtraction inside there, because that would have been a binomial or trinomial.
Let's say there is a subtraction in there.
Mhm.
So how would you still do that?
Good question.
Sorry, I'm curious.
No, that's fine. If there was some sort of addition or subtraction in there, that's going to be where we have to go through this process.
Okay.
So instead of distributing the exponent, you have to write out that base however many times the exponent tells you to.
Okay.
Yep. So it changes kind of how you're using multiplication. And in this case, since it's just a monomial, all you're really doing is sharing that exponent with each individual base. Now, what I'm going to do next is I'm going to go ahead and clean up that numerator a little bit more, because technically I still have parentheses there. And can I actually calculate or evaluate 3 to the power of 2?
3 times 3.
3 times 3, which would give me
9.
9. So 3 to the power of 2 gives me 9. Do you remember what we do when we have a base with more than one exponent?
What's multiplication?
It would actually be multiply then. So here we would get x to the power of 10 and y to the power of 6. So this is where some of the confusion comes in. You add the exponents when you're multiplying the bases, but if the base is raised to 2 different exponents, you multiply those instead. It's kind of a head scratcher, but we have if you go back to one of those earlier lessons, there's a few examples there that you can take a look at. So again, I'm still bringing that denominator along for the ride. We're not quite ready for it, or at least not until right now, because what I do see is that I do now have common bases of x and bases of y. So what I'm going to do is divide them. Now, does 9 have anything to divide with?
No.
No, so it's going to stay 9. X to the 10th divided by x to the 10th, guess what that becomes? When you're dividing, you subtract the exponents. 10 minus 10 would be?
9. 10 minus 10 is 0.
I thought you said 9.
I said
It's like,
9.
it would be none. So there would be no more x's left. What about y to the 6th divided by y to the 8th?
It'd be -2.
It would be -2. So I would have y to the power of -2. So what I've done so far, if you think about that little list I mentioned earlier, is in a couple steps, we took care of all the parentheses. And this step right here that we just completed, we took care to make sure that each base only appeared once. One of them happened to disappear altogether. That happens sometimes. But now we're left with an issue that we have a negative exponent.
Would you put it over one and then put the y and make down?
Absolutely.
Fraction?
So I needed to look like a fraction, so I'd put the whole thing over one, and then I would move the base that has the negative exponent, so the y to the negative second, I would move it to the opposite side of the fraction that it's currently located on. So when it's all said and done, what's left on top?
9.
A 9, because it was happy where it was at. And what is now on the bottom?
Y to the second power.
Y to the second power. So my final solution is 9 over y squared. So if you kind of go through that same process, knock out the parentheses, combine the common bases, and then if you have any negative exponents at the end, take care of those, you should be set. All right, number 31. 31, you'll notice has a little bit of space here, which is going to involve some work. 31 says that you are running the concession stand at a local movie theater. You are selling popcorn and candy. Each bag of popcorn costs $2.50, and each candy bar costs $1.25. At the end of the night, you earn a total of $55, selling a total of 32 items. Write a system of equations to help solve how many bags of popcorn and candy bars you sold. Be sure to define your variables. So a situation like this isn't too unheard of. Maybe at the end of the night, the register prints off a slip and all it tells you is how much you earned in total and how many items you sold in total. It doesn't actually give you an itemized list that tells you how many of each item. So in theory, if I wanted to make sure I could go back and track my inventory accordingly, I would have to do a quick computation like this, or maybe set up a spreadsheet. Once I understood how this one works, I could set up a spreadsheet to do the same thing. But you gotta know the basics like this before you can do something fancy like spreadsheets. Now it did say be sure to define your variables first. I'm gonna kind of take a shortcut here. I'm gonna come down here to my answer lines, and I'm gonna say that the number of bags of popcorn sold, I'm gonna put an X next to that. So I know anywhere that I'm talking about bags of popcorn sold, I can use X. And then I'm going to say the number of candy bars sold will be my Y. So that is essentially me defining my variables in a slightly lazy fashion. But then I come up here to the word problem, and now I need to come up with two equations in order to be able to solve how many of each item was sold. So what do you notice about the values we were given? Do they have anything in common? Do they all have something in common? I'll give you a clue. You're fine. I'll give you a clue. These three values have something in common. The $2.50, the $1.25, and the $55. They're all money. So three of the values all are describing money, and they all kind of relate together because the individual prices is what added up to the total price. So we could write an equation that says that that night you earned $2.50 per what?
X.
Per X. X is the number of bags of popcorn sold. In addition to that, so plus you earn $1.25 per what?
Y.
Per Y, per candy bar sold. And at the end of the night equals the total of 55. Looking good so far. But then we have this fourth value here, 32 items. That's not measuring money. Think about it, that's measuring quantity. What made up that total of 32 items?
X and Y.
X and Y. All the X, all the bags of popcorn, plus all the Y, all the candy bars sold, came up to a total of 32 items. So I would write X plus Y equals 32. And just like that, we have now created our own system of equations. Now I need to use that system of equations to actually solve. Now you actually have two choices here. I would argue that substitution or elimination both would work relatively well. So I'm going to leave it to you guys to decide for me. Would you rather use substitution or elimination? Substitution? Why substitution? You have no idea.
I wasn't here for the lesson.
So for substitution, I will tell you that it does help for one of the variables to be by itself. Now that's not already done for me, but if you look at the second equation, we could move one of those pieces relatively quickly. So do you want to do substitution?
Yeah.
Okay. Do you want to get the X or the Y by itself?
I said why.
Because
Why?
because we've spent so much time getting Y's by itself, that's fine. So to do that, I would have to subtract the X from both sides. And that would leave me with Y equals, they're not like terms, so I'm just going to write 32 minus X. Now, here's the great thing about this. Anywhere now that I see a Y, what can I replace it with?
The 1 or 32 minus X.
32 minus X. That can now behave as my Y. Well, if I think about it, I have a second equation. How much space do I have? Oh, plenty of space. I have a second equation that has a Y in it. So if I take the top equation, and when I get to the Y, I replace it with 32 minus X, I should be able to get an equation that I can then solve. So what that would look like is we'd have 250 or 2.50X plus 1.25, but instead of Y, I'm going to drop in my parentheses, fill it with the 32 minus X, close the parentheses, and write my equals 55. Good news. I should be able to solve that new equation. So taking a look here at this one, what should catch your eye first? Parentheses. So the 250X is going to drop down. What's 1.25 times 32?
40.
40, okay. So plus 40. And 1.25 times a negative X?
Negative 1.25X.
Negative 1.25X. Bring down my equals. Bring down my 55. After parentheses, what do I check for first? Or next, I should say.
Like term.
Like terms. Do I have any?
Yes.
What do I have?
250.
The 250X and the $1.20 minus $1.25X. If I were to combine those, what would I get? $1.25X plus the 40 drops on down, still equals 55. Do I have the variable on both sides? No. So now that's all that's left is to get that variable by itself. What would you do next?
Minus the 40.
Minus the 40 from both sides. So 40 minus 40 is gone on the left, leave me with 1.25X equals 55 minus 40, I believe is 15. And then how would you finish solving this?
Divide by the 125.
Divide by the 125. Don't leave out that decimal that will affect your division. You get 12. X equals 12. And that's good news because X was one of the things we were looking for. What did it represent?
Popcorn.
Popcorn. So down here, number of bags of popcorn sold is 12. Now we're not done. We still need the Y. Now here's the neat thing. Don't I already have an equation where Y is by itself?
Yeah.
Sure. I can bring this right over here and rewrite this Y equals 32 minus X to say Y equals 32 minus my X, which is 12. What is 32 minus 12?
20.
Which makes sense because 20 candy bars and 12 bags of popcorn would give me a total of 32 items. And if I wanted to go one step further, I could check to see if I charged $2.50 times 12 plus $1.25 times 20, odds are you'd come up with the $55 that you ended up with at the end of the night. Good. So this problem could have also been solved with elimination. If you prefer elimination, if you're more successful with it, you should still get the same results. So that was our system of equations. Moving on to our next page. This one, we didn't get a chance to evaluate graphs specifically, but I think with a little bit of common sense, we should be able to come to the conclusions necessary to answer the 3 questions provided. So what we've been given is a graph, and it's representing this story where a woman is riding her bike home after visiting a local park. The travel graph below represents that woman's journey. So some things that you typically want to do in this situation is first see what's being measured. And in this case, our y-axis, which are going by units of 1, is the distance of this woman from her home measured in miles. So 1, 2, 3, 4, 5, 6, 7, 8. Looks like she's starting 8 miles from home. Okay. The second thing being measured on the x-axis is time. And it appears that this time is being measured in minutes. And it looks like it's going by increments of 10. Keep in mind, every 60 minutes equals an hour, if you need that as well. So we have a series of questions here that we want to describe or answer accordingly by using the graph provided. So 32A asks us to describe a scenario to explain what is happening in section B. Well, section B is right here. What would you describe the graph as doing?
Standing still, so to speak.
Okay, it's interesting that you use that, standing still, because ironically, that's probably exactly what she's doing. 40 miles?
Minutes.
Or 40 minutes? Well, B doesn't just go at 40 minutes. B started at 30 minutes into her ride and lasted until 50 minutes into her ride for a total of how many minutes? From 30 to 50?
80 minutes.
30 to 50
Oh.
would be 20 minutes. So for 20 minutes, Leanna, you said that she was standing still. And if you think about it, that's literally what's happening, because what is her distance at 30 minutes from home? 6 miles. And for that whole time, all the way up till 50 minutes, her distance is still 6 miles. Well, if her distance is not changing, she's not getting any further away. She's not getting any closer. Therefore, she must be standing still. So we could say she wasn't moving for how long did we say?
20 minutes.
For 20 minutes. Now, if you want to be fancy, you could say maybe she stopped to take a break, had a drink of water. stopped at an ice cream parlor, was enjoying some ice cream. Again, add story to it if you wish, but for our purposes, maybe this is Tammy. For our purposes, we can just very simply say she wasn't moving for those 20 minutes. That's why her distance did not change. 32B, what is the woman's speed during section A? Now, if you think about speed in a car, you have two measurements, miles and hours. Well, in this case, we're going in minutes. How many miles did she travel in A?
75.
Where are you getting 75?
It's between 7 and 8.
It's between 7 and 8.
Yeah.
Well, if you think about it, A starts at 8 and ends at 6. So how far does she travel? What's your change in distance? 8 to 6. 2 miles. What's your change in time? 30 minutes. Oh, I'm sorry. So in that time, she traveled 2 miles in 30 minutes. Now, technically, that is a speed, 2 miles per 30 minutes. If I wanted something more familiar, I could convert this to miles per hour. So think about it. If she traveled 2 miles in half an hour, if she kept up that pace for another half hour, how far would she travel? If you just doubled it.
4 miles and 16.
Theoretically, 4 miles and 60 minutes or 4 miles per hour. Either one would be correct, though. Last question. How long did it take the woman to reach home?
90 minutes.
Why do you say 90 minutes?
Because that's when it stops, I think. I don't
That's,
know.
well,
I cannot see.
very literally, that is when the graph stops. But let me ask you, at 90 minutes, how far was she from home?
0.
0 miles. That must mean she's at home. So 90 minutes is how long it took her, an hour and a half. Good. So not really any math to be involved there. Really, it's just identification. All right. Last page, if you can believe it. Now, here's the good news. The last page has 3 parts, but because of our time, we didn't have time to do enough of the information to do 33A. We didn't have enough time to learn about 33B. You'll be doing all that with Andrea in Algebra 2, and it really helps when you learn how to graph these quadratic equations that we've spent a lot of time solving. What we do have enough information to do, however, is 33C. So let's come back up here to the prompt. It says that Jason jumped off of a cliff into the ocean in Acapulco while vacationing with some friends. His height as a function of time could be modeled by the function h of t. So that's the height, which is equal to negative 16t squared plus 16t plus 480, where t is the time in seconds and h is the height in feet. So let me bring it down here. H of t equals negative 16t squared plus 16t plus 480. And the question is, Jason hit the water after how many seconds? So in other words, what are we solving for? H of t. We're solving for t. In order for us to be able to solve for t, we better know something about the height. If this function is measuring his height above the water, what is his height above the water the moment he hits the water? 0, because that means he's literally on the water. So I can replace the h of t with 0. So I get 0 equals negative 16t squared plus 16t plus 480. And just like that, we have a quadratic equation, which I believe if someone could fact check for me, on page 1, didn't we have solving quadratic equations?
Factor, yes.
Okay, so I'll make a little note up here. Page 1, solving quadratic
It's question 2, if you wanted to.
equations. Question number 2,
Yeah.
if you want specifics. Hopefully you've jotted it down from last week. You have those steps. If not, it's in the video as well. So page 1, solving quadratic equations. I'll kind of talk through it anyways. First thing you really like to happen is you'd like your equation to be set equal to 0. Well, considering the scenario we're looking at, it is already set equal to 0, which is convenient. Step 2 is to factor. So I'm thinking asterisk method, but even before the asterisk method, what should you always check for first?
Greatest common factor.
And I do believe that there is one that we can factor out here. And Leanna's telling me that there's a 16 that we can take out. So let's do that. Let's factor out a 16 from each of these. So we're going to get 0 equals 16 is going to come out, the greatest common factor, before I divide. Negative 16t squared divided by 16 is going to leave me with a negative 1t squared. 16t divided by 16 is going to leave me with a positive 1t. And 480 divided by 16
30.
is 30. Leanna's telling me. Good. Now, with that 16 out of the way, off to the side, now I would say asterisk method would be a good bet. So let's go ahead. What's our A going to be now?
-1.
A negative 1. What's our B?
1.
Positive 1. And our C is 30. So I'm going to have to work a little bit more horizontally here. So off to the right, I'm going to set up my asterisk. So A times C on top, we're looking at a negative 1 times 30, which is a negative 30. On either side is A, which are negative 1s. On the bottom is B, which is a positive 1. So we should have a positive 1 on the bottom. So I need two factors of negative 30 that also happen to add to equal positive 1.
6 times 5.
6 times 5, okay. Now I need a negative,
6.
so you're saying negative 6? You sure? I think the 5 needs to be negative, because 6 plus a negative 5 would give you that positive 1 we're looking for on the bottom. Now, do either of these simplify?
No.
Well, not quite the way we expect, but anytime we see a double negative, what do we usually do?
Turn up positive.
Turn it positive. So that negative 1 over negative 5, I would suggest go ahead and make that positive 1 over positive 5. Bring down the variables t. Those are going to go on top. And I'm going to have to jump over here to the right a little bit and rewrite my equation, which is going to be 0 equals the greatest common factor 16 times the binomials negative 1t plus 6 and 1t plus 5. So that was the factoring step for solving quadratic equations. After it's factored, thanks to the zero product property, now we can consider what would have to happen in order for one of these to be zero themselves. So we can come up with the conclusion either 16 has to equal 0, which, can we just drop that one out?
Yeah.
Because of course 16 cannot equal 0. So it was important for factoring, but it won't give me a solution. Or negative 1t plus 6 has to equal 0. Or t plus 5 has to equal 0. How would you solve the first?
Oh, -6.
Subtract 6 from both sides. So it leaves me with negative 1t equals negative 6. Then what?
Divide by the -1.
Divide both sides by negative 1. And I end up getting t equals a positive 6. How would you solve the second one?
-5.
Subtract 5 from both sides. I get t equals
-5.
-5. And so now I have found two solutions. But wait, there was a story attached to this. And t actually represented something. In this case, time. And Leanna, I heard you say it softly. Time cannot be negative. And therefore, although the -5 is a good answer for the equation, it is not a good answer for the story. So the only thing left then is the 6, which means that it must have taken Jason a total of 6 seconds from the moment he jumped to hit the surface of the water. Which, for those out there who are extra bright, that's a long time, and Jason is probably no more. Because if you were to actually pick apart this function, there's a little trick that the constant is his position before his jump. So he was 480 feet up. That's 48 floors at least. 30 foot. Great. That's like 3-story building. Jason here jumped off of a 48-story building. He's probably not alive anymore. But I didn't say it was a good story, but it allowed us to do some good math.
You learn what cement feels like. Water feels like cement.